Okay. Allotropes, different structural arrangements of an element. So for example, all of these are carbon atoms, and they are all attached to 1, 2, 3, 4 other carbon atoms. And the shape of the bonds around the carbon atoms is that little tripod shape. Do you remember us talking about that? Do you remember what shape that's called? Tetrahedral, okay? This is diamond, okay? So, you know, put it on a ring, very lovely. Now this is not diamond, but it's also made of carbon. But you see, each carbon is now only attached to 3 other carbons. They are all double bonded like a benzene, where it's like double bond, single bond, double bond, single bond, double bond, single bond. And so you do end up with that resonance structure. They're all one and a half bonded actually, because it goes double, single, single, double, single. So yeah, 3 out of 6. So 1.5 bonds. So the bond order would be 1.5. Okay. So this is graphite. And you can see it comes in layers. Now this fourth bond is not really a bond. These are, but of course I can't have them just hover over top of one another, right? That wouldn't work very well, right? It has to have a support. These are actually intermolecular forces in between the layers of the graphite sheets. Okay, so there are, in this model of graphite, how many layers are there? 3 layers. And in between the 3 layers, what do we have? Intermolecular forces. So intermolecular forces, are they strong or are they weak? They're weak. So let's imagine, where would you find graphite, by the way? You would find it in your pencil. So if I was to take my pencil, okay, you know how I had my ring before, this is now my pencil. Now, there are going to be intermolecular forces between the desk and the graphite sheet. So if I start to write with my big, huge pencil, what will happen is that a layer or 2 will rub off and stick to the counter and will shear off because as these intermolecular forces break. Isn't that cool? I know, right? So we're breaking off layers. It's not necessarily like a single layer, but it might be, 3 or 4 layers or whatever. I don't know. But yeah, that's how it works. So, allotropes, different, this needs fixing, doesn't it? It wants to come apart. Different structural arrangements of an element. So when we have phosphorus, we have a white version of phosphorus and we have a red version of phosphorus. These 2 are different allotropes of phosphorus. Okay, now technically this has nothing to do with this unit, but at some point you need to learn the word, so we might as well learn it now. We'll refer back to it later on. It's not going to be on the test. So the word allotrope is not on the test. They'll have different colors just because of different bonding arrangements. So if there are double bonds in certain things, it will cause different like electron resonations and stuff. It causes like yeah. We're gonna go into that maybe at sometime in the future, but not today. Okay. Metals are non-lustrous. Non-lustrous. Non-metals. Sorry, I cut and pasted. Non-metals. Lustrous means shiny. Okay, so if you say something has luster, it has shine. Is it R-E or E-R? R-E. Okay. They are poor conductors of heat and electricity. There is an exception to that. Electricity is moving electrons, right? Now, in my graphite, do you remember I've got a double bond, single bond, double bond, single bond? And what are those electrons doing? They are resonating, yes? So they're just kind of all the way around. So they are not localized to one bond, they are delocalized on all of the bonds, which means that if you put a positive terminal here and a negative terminal here, the electrons are actually going to flow from one end to the other. So graphite will actually conduct electricity, but only in the direction of the sheets, in the direction of the layers. It won't conduct this way, but it will conduct this way because of those delocalized double bonds. Okay? So have you ever like attached, like when you're in grade 9 or something, did you ever like see if your pencil lead could conduct electricity? No? Okay, well, we might do it this year. Okay. So nonmetals are non-lustrous. They are poor conductors of heat and electricity, with the exception of graphite in the one direction. They have lower melting points and lower densities than metals. Their solids are brittle. What does it mean to be brittle? They're breakable. Yes. Nonmetals tend to have low ionization energies. Yes? Does it make sense that they have low ionization energies? Are we all just off in La La Land this afternoon? We could do it today. Or we could wait until our other people are back, because we're still missing 2 people. It'll go bang. We'll do it sometime within the next week. Maybe today. I know. Nathan and Aaron, what can you do? Okay. Nonmetals tend to have low ionization energies. Does that make sense? Because they're up in the top, right? So what is the charge density? Charge density. That means the amount of charge, the amount of positive charge per size, per volume. Charge density is high because the atom is small up in the top right corner. Yes, atoms are small in the top right corner, and they have a larger nuclear charge as we go further to the right because Zep increases. Is good? Like, I'm ready to smack these people. They're really distracting. What's that? Oh. There we go. Yep. right? They do not tend to form cations. Per unit volume. It's just kind of combining Zeph and ion size together. Okay. Nonmetals tend to form what kind of ions? They do not tend to form cations, they tend to form anions. Or sometimes oxy anions, that would be like ClO3 or NO3 in solution. Don't get too excited about anything there, it's just sort of there because it was on the list. Nonmetals have a high negative electron affinity. So they tend to be, and this is one of those words we learned yesterday, reduced. They tend to be reduced. In other words, they don't lose electrons, they gain electrons. Remember, Leo the lion says, grr. Is this on this test? No, this is not on this test. I'm just introducing the terms because we're going to see them as we go along. Non-metallic character, very straightforward. Oh my God. I'm tired of talking over everybody. It's hard. Non-metallic character increases to the right, it increases towards the top. It's bad enough that I have to talk over them. God, I don't know what they're doing in there. There's much thumping and yelling. Reactivity. Whereas yesterday we looked at metals which were losing electrons in order to react, today we are looking at nonmetals which are gaining electrons in order to react. So we want things that are good at gaining electrons. Where would we find those on the periodic table? Where would we find things that are good at gaining electrons on the periodic table? Top right, okay? So as we move from left to right, oops, that's supposed to be a highlighter, the reactivity of the nonmetals increases. The nuclear charge increases, the number of energy levels stays the same. Is this starting to sound very, very familiar? Okay, and therefore we have a stronger attraction for the electron as we move to the right. Therefore, nonmetals are more likely to react, in other words, accept electrons as we move to the right. As you move up, also the reactivity increases. Why is it increasing as we move up a column? What's changing as we move up a column? There's less occupied shells, and therefore any electron that is coming in is going to be able to get closer to the nucleus, which will make it more stable, which means it's a more favorable position to be in, which means it's going to be more likely to occur. Okay, and here's the real bit that I wanted to get to. Non-metal, what do you remember about metal oxides? Metal oxides were what did we get when we reacted a metal oxide with water? We got a base. What do you think we're going to get when we react a non-metal oxide with water? We're going to get an acid. So we take a non-metal oxide, like let's say CO2. There's our non-metal with oxygen. And we put it with water, H2O. And if we just take all the atoms from the H2O and all the atoms from the CO2 and smush them together into one formula, what do we get? We get H2C, and what else do we have? Oxygen. How many oxygen do we have on the left? 3. How many do we have over here? 3. So we have H2, we have 1 C, and we have 3 oxygens. Normally, when you're predicting the products of a reaction like this, you just smush everything together into one formula. Yeah? Now, sometimes you'll get one where you're like, oh, what am I going to do with this? I cannot smush that together very well. Okay? I don't think it's going to ever come up, but just in case it does, what you're going to do is you're going to say, who is the most common oxyanion? That's almost always going to be the 8 anion. Let's just say always. Okay, so who is the 8 ion that is based on phosphorus? Phosphate. So what we're going to do is we're going to say, okay, in this case we have phosphate, PO4, 3 minus, and we need to form an acid with that, yes? So how many H's would we need in our acid? 3. Okay, so we have H3PO4. Now I've balanced it here, but let's assume we hadn't balanced it. P2O5 plus H2O gives H3PO4. And let's assume that if I've done this, I'm just gonna cross my fingers and hope that everything works out well and I will be able to balance it. Okay? What would be the first thing I might balance here? I would tend to balance the P because it's not oxygen or hydrogen. So let's put a 2 here and see where that takes us. Now I have 6 hydrogen. So what could I do to fix that? Put a 3 here. That gives me 6 hydrogen. And it also gives me 3 plus 5 is 8 oxygen. And lo and behold, guess what I have over here? 8 oxygen. So if you do that, like honestly, like I said, I don't think it's going to come up. I think it's all going to be like smush this together with that into one compound and you'll get your product. But just in case, this other one will do you. All right, so take a couple minutes and just try these questions here. When you are done, now I'm a little bit unhappy because I did not manage to get the duo tanks. Because I worked for 13 hours yesterday, so I did not go to Staples. I'm going to Staples tonight to get the duo tanks for unit 11. So you can either just stick this in the back of your unit 10 for today and change it over tomorrow, or you can put it in your binder or whatever you like. I'm going to trust you to be clever about it. Can I do that? I saw one person nodding. That's excellent. 3 people. Excellent. Good. They are here. So when you're done, come pick one up. And they don't have page numbers, so you can start numbering your pages from energetics and covalent bonding as page 1. I don't know how I managed to do it without page numbers. Probably because I was working for 13 hours and I got a little burnt out. Hi.
There's like this one where it's metal.
Yep.
Why is there no?
There isn't. Nitrogen won't react with water. Like if you bubble it in, it just sits there and does nothing. Yeah. They're very stable on their own. Yeah. Nitrogen already has its outer shell completely fulfilled by the covalent bond it has with the other nitrogen atom, whereas sodium still has an electron in its outer shell. Right? Does that make sense? So again, like oxygen has a full outer shell, so it doesn't need to react with water, whereas calcium has 2 electrons in its valence shell, and it would want to give them to somebody, like water. Yeah.
I'm gonna have a test on this before the break.
This? No. We won't make it. No.
This is probably going to be like, oh, are we going to review it when we come back?
Oh God, yeah. Oh yeah. Oh yeah. You guys can bet on what color duotang I've got. I know some of you like to make bets on that sort of thing. That goes in wherever you need to keep it until tomorrow when we get our own duotang with its own color. If anyone would like a paper clip for it, there are paper clips. A tetrahedron? And don't forget to number your pages. Take a moment and number your pages, because I was stupid and I did not number them for you. And then I'd run them off and I'm like, well, I can't print them out again. That would just be so wasteful. We are going to do some energetics of bonding today. Yeah. We're going to do the experiment. I'm going to wait till everybody's back to do the experiment. I just would feel bad if they missed it. It's quite short anyway, so even if we were to, yeah. We'll do it tomorrow, Thursday. No, not Thursday, because Thursday we have Mountain Madness. Oh, those of you who are in grade 10, you don't need a field trip form for Mountain Madness, I don't think. You just need to go when you go, but I think that you're not the same block, am I right? So it doesn't matter anyway. Okay, gotcha. Hmm? Skip day is the stupidest day. This is like freaking every day is skip day for grade 12s. Let me tell you, if you skip during AP chemistry, I will have your head on a platter. Will not be happy. What? But we're in semester 1, right? So it's okay. There is no such thing as skip day. Skip day isn't a real day. It's a made up thing that people do because they don't want to come to school. Grade 12 sometimes come up with like a skip day because they're like, oh, we're grade 12s and this is what we do. The semester 2, yeah. Oh, yeah, no. But it doesn't matter because I won't teach you in semester 2 anyway, so you can just be like, okay, I'll skip for people who aren't Ms. Spence because I know it would piss her off, but it's okay. They have a day when they say it's skip day, but that's nonsense.
I remember that because I was like the only person in my room.
Yep.
Grade 11, 12, no. Well, Mr. Buddha is just nice. You get it.
Mr. Badai is awesome. He was one of the original people at the school as well, although he left for a while and came back. How are we doing? Are we ready for energetics of covalent bonding, or do we need a minute? We're ready? We need a minute. Okay, take a minute. Yeah. Oh, I'm so sorry. Yeah, I'll fix that. Thank you. Hi.
Why do you use that HNO3?
Because NO3 minus has a -1 charge. Oh. Hi.
Wait, why isn't this added? Because are we doing like that? So aren't they supposed to be added?
Oh, that should be added.
That should be added, right?
Yeah,
Okay.
it's because I was cutting and pasting. Yes.
So are we restriction on the test?
Yes. Ooh, back here, I made another boo-boo. Back in the non-metals. So it is, just get rid of this line. Oh, over examples for reactivity of non-metals. And also there's a 6 missing here. Hi.
Like oxidation number?
No.
No? Yes.
You do not need to know oxidation number. No, no, no. Do you know we only have 7.5 more days of school?
I feel like teachers come.
Yes, we do, because we are more desperate. This is when we ponder the wisdom of taking a job with homework. It's like, what was I thinking? The missing 6 is in number 5.
And then you don't because you're a mean brother. He wants to talk to you out of your
Are we ready for bonding? Yes. I heard one person say yes. I heard nobody say no. We're ready. Excellent. Okay. The covalent HH bond is the one we're going to focus on to start with because it is the most simple. There is only one proton and one electron. So in the nucleus, we have a positive charge. This is the new stuff. If you didn't get the new stuff, it's on the front table there on the right-hand side. Anyone else not get the new stuff? We're good? Okay. So look at this nucleus. What's it doing to the nucleus of the other atom? What does nucleus A do to nucleus B? Nucleus A repels nucleus B. So we have nucleus, nucleus repulsion. Okay? Now, look, we have also our electrons in the cloud out here, right? So we have negative and we have negative. What are those electron clouds doing to each other? They are repelling, so we have electron-electron repulsion. So we have two repulsive forces, but then we have the electron cloud looking at the nucleus of the other atom and saying, ooh, that looks good. And then the electron cloud of atom B looking at the proton of the other atom and saying, oh, that looks good. So we have nucleus electron attraction. So three different forces, two repulsions, two attractions. And all of these forces together balance out to give a net attractive force that holds the atoms together to form an H2 molecule. But there is a perfect distance at which those forces are in perfect balance. Yes? If they're too far away, they will still be more attracted to each other and they'll want to come together. But if you start pushing them too close together, then the repulsive forces start to take over and they'll spring back from being forced closer together. So here's the energetics of a covalent bond. Two hydrogen atoms, okay? This is 10 angstroms apart. Do you guys know what an angstrom is? That is 10 to the negative 10 meters. Okay, so that's an angstrom. So that's what we have down here is 10 angstroms. So at a 10 angstrom distance, nothing happens. They're too far away. So here we have the man pushing them to a 8 angstrom distance. And once they get there, they're like, those attractive forces start taking effect. Okay? And the atoms will just start moving towards one another. It's like if you have a couple of magnets, if you put one on this side of the table and one on that side of the table, they're not going to do anything, right? But if you put two of them fairly close together, what are they going to do? They'll whoop, go and attach to one another. Okay? Now, they move together, we get a big bang. Okay? Why do we get a big bang? Because bond formation is exothermic. And then we finally end up with an H2 molecule. And the distance between the two nuclei is called the internuclear distance. Inter meaning between, nuclei meaning nuclei. So this distance here is the internuclear distance. Inter, of course, meaning between. And when a hydrogen molecule has an internuclear distance of 0.74 angstroms, that is its perfect distance. It can do a little bit of, the stretch contract kind of thing. It can do that kind of vibrating motion, but it will always average out at about 0.74. Okay? Is good? Okay, so here is a diagram, and we're going to start over here. Because over here, at this point, the two atoms are sufficiently far apart. So this is the internuclear distance along the x-axis. So if we're far over to the right, that is a large internuclear distance, yes? So they have no interaction. So what we're graphing on the y-axis, the potential energy generated by those two atoms is 0 because they don't have any interaction. If there's no interaction, they can't be affecting each other's energy. Yes? But as they start to come closer together, they begin to attract. And if there's an attractive force, the potential energy goes down as they move closer together. It's just like there is an attractive force between this pen and the Earth, and so the potential energy gets lower as the two get closer together. Yes? Okay, so those two are moving closer together and they're attracted to one another, and so the potential energy decreases. Just like the potential energy of the pen decreases as it gets closer to the Earth. And as we continue to go closer and closer and closer and closer, we get a lower and lower and lower potential energy, right? Just like as the pen gets closer and closer and closer and closer to the Earth, it gets a continually lower and lower and lower potential energy. But this is where our model breaks down because there is no repulsive force between the pen and the ground, right? We just have an attractive force. So that's where this model kind of breaks down. So eventually we get to the lowest potential energy point. So the two protons, or sorry, the two atoms have been attracting each other, and they're like, woo, falling into a potential energy well, yes? But now they get close enough that the electron cloud starts to repel the electron cloud, and the nucleus of the one starts to repel the nucleus of the other. So they get lower, and then all of a sudden, oh, if I try and force them together, right? And I might fire them at each other with a lot of energy, right? I might be like, wah, right? But they will eventually like settle out to their perfect distance. So you can force them closer together, but it does require an input of energy, okay? Now, we have a symbol for the internuclear distance, which is 74 nanometers, or 7.4, what was it? No, it's 0.74 angstroms, which means it's 74 watts. That just doesn't seem right to me. Picometers, okay, 74 picometers, sure. I'm not gonna argue, whoever made this must know what they're doing. Okay, so 74 picometers. And because you know me, I love my graphs, I love my visuals. So here's just another visual. You can see they're far apart. Now they're closer. And so the potential energy is, when they're further, the potential energy is higher. When we get closer, the potential energy is lower. And then when we get the bond forming, we get the lowest potential energy. And then why does it start to go up again? Nuclear repulsions, okay? So all this little section over here, all of this is due to nuclear electron attraction. So that whole like getting closer business. Yes. I'm sure it is, but we just don't talk about it very much, so I'm just going to avoid that. Yeah. So we kind of ignore the electron repulsion here, so we're just gonna gloss. We're gonna gloss right over that. Yeah. Yeah. All right. Now, as the bond forms, the potential energy gets lower. Therefore, the system is doing what? Is it absorbing energy or releasing energy? Ooh, that's tricky. Talk with your partner about that one. Not during the bond formation process. It only gets higher if you squash them together further. All right, so the potential energy gets lower. What is happening? Is the system absorbing or releasing energy? Releasing. Therefore, bond formation is exothermic. Conversely, bond dissociation or bond breaking is endothermic. Don't you love how all these ideas come back? You're like, yeah, maybe, sure. And then I just put this one in here because I wanted, I have trouble saying no to a good diagram. You can take a look at it. Now, the key thing here is that each electron, the electrons spend most of their time in between the nuclei. Why do they want to be there? Because if they're over here, they're farther away from that one. right? If we have an electron that's way over here, it's farther away from the other one. So it's the most stable right in the middle. Okay, so they mostly spend time between the nuclei, although sometimes they spend time other places, right? You will have electrons all over the place. There are some exercises here. We're going to leave that for now, though. And actually, I don't want to do this one today because that's more of like a full class kind of thing. We're going to go to 11.1c, which if you had page numbers would be on page 13. Just go to the end of 11.1b. Greek letter sigma. You draw it like this. Draw one with me, like that. This is a small sigma, lowercase sigma. And hopefully you all know pi. This again is a lowercase pi. This is on page 13, so if you go to after 11.1b, no, but if you look at the top of the page, it says 11.1b, then it'll say 11.1c. Yeah. So there are two different kinds of bonds. One is called a sigma bond, and one is called a pi bond. Sigma bonds are first bonds. So if you have a single bonds are always sigma bonds. It's nice that they sound similar, yes? Single bonds are sigma bonds are single bonds, except that the first bond in a double bond is also a sigma. Okay? First bond in a double bond is a sigma bond. The second bond in a double bond is a pi. If you have a triple bond, the first bond is a sigma, the second bond is a pi, and the third bond is a pi. So we have either sigma, sigma, pi, and then we have a triple bond, which is sigma, pi, pi. Why are they called that? I don't know. I guess. Well, there's, no, I do know, because when s orbitals overlap, you get a sigma bond, S for sigma. When p's overlap, you get a pi bond. Now, those are not, it's not limited to those, but those are sort of the most basic state, okay? Well, let's take a look. First of all, sigma bond. It is a covalent bond in which the highest electron density, which you can see by this little red cloud here, where is it the most dense? Between the nuclei, along the internuclear axis. So, where is our greatest area of electron density? Between the nuclei along the internuclear axis. So, all single bonds, not some of them, all of them, are sigma bonds. The first bonds in a double or triple bond is a sigma bond. Now, anything that is on the end of a sigma bond is free to rotate. So it's like this pen cap, I can rotate it, yes? So that's like if I have a sigma bond, anything that's on the end can spin. Okay, and I'll bring in some, we don't really have time for it today, but next day I'll bring in some molecular models so you can see what it looks like when things spin. You can have, now remember I said it was with s orbitals, so yes, you can have an s orbital overlapping with another s orbital, and that will give you a sigma bond. Here we have it occurring with hydrogen. There's an s orbital and an s orbital, and now we have a sigma bond. But you can also get a sigma bond if we take an s orbital and we overlap it with one end of a p orbital. That is also a sigma bond. So an s plus a p gives you a sigma bond. And you can see where are the electrons? They are in between the nuclei. Yes, here are our electrons on the internuclear axis. Yes. We could also, and I know I said that p orbitals gave pi bonds, but there is one case where they can form a sigma bond, and it's when you have head-on overlap. That's what we call it when they overlap like this. Okay? Head-on overlap. As opposed to if you have two of them that are oriented like this, you end up with the top part of the lobe overlapping and the bottom part of the lobe interacting, and then you have that node in the middle where there is no interaction. Okay? Yeah, but if you look, this one, they overlap each other. Where is the electron density? Along the internuclear axis. Therefore, it's a sigma bond. Now, here's a pi bond. Here's nucleus 1. Here's nucleus 2. And these are where the electrons live. Where do they live? Do they live along the internuclear axis? No, they are above and below the internuclear axis. So on opposite sides of the internuclear axis. So for example, above and below. Now, just like when we had a p orbital, how many orbitals is that? How many p orbitals is this? Is that 2 p orbitals? Is it 3 p orbitals? Is it 1 p orbital? That is 1 p orbital. And if we overlap it with another p orbital, we have formed 1 pi bond. Okay, so we get our overlap area here, we get our overlap area here. 1 pi bond. So even though it has 2 lobes, it is a I can't use the word single bond because it's not a single bond. It would be the second bond of a double bond, but you only have one bond. So these two lobes together make one bond. Why doesn't it wish? Oh, because maybe you've already taken up that direction, right? You might have this overlap and then have like the other ones just sitting here and they need to also overlap. So you've got some going this way, some going this way. Yes? No, nothing to do with the number pi. So you can get these bonds either from p orbitals overlapping, because of course then you get the p overlapping with the p, which gives you the two lobes there. Or you can have a d orbital overlapping. Have I not shown a d orbital overlapping? Apparently I haven't, but there is one later on, so don't fret. The second and third bonds are always pi bonds in a double or triple bond. So here's ethane, an alkane. Remember when we have alkanes, they have only single bonds, okay? That's a sigma bond, sigma. When we have ethene, that's an alkene. Alkenes have double bonds. Carbon, carbon double bonds if you have an alkene. And because we have one sigma bond, that other bond is going to be a pi bond. And now finally we get into our alkynes, and when we have an alkyne, that means we have a C triple bond. So we have one of those bonds is a sigma. What are the other two? Pi. So what you have is you have sigma. This is one orientation, right? And then 90 degrees to that, you have this pi. And then what's at 90 degrees to that? Pi. So you have sigma, pi, pi. Everyone do it with me. Sigma, pi, pi. Again. Sigma, pi, pi. Again. Sigma, pi, pi. Sigma, pi, pi. Doesn't it sound like I'm inducting you into some fraternal cult or something? Sigma, pi, pi. Sigma, pi, pi. Now we just need robes and candles and some like hazing ritual. Yes?
Right, so I can understand how they relate to S and P.
Yes.
I still don't know why they're the same.
Well, well, no, because the sigma is the letter, Greek letter S, and pi is the Greek letter P.
Oh,
Yeah. Yeah. Okay, so we'll leave this for today because you guys sound like you're done, and I'm quite frankly, I'm done too. For homework, you could do the exercises in the energetics of covalent bonding. Okay, I'll bring you guys some more review material for your thing. Oh, did you want to take that Lewis quiz with you today? It unfortunately did not double side, which irritates me no end. Where did they go? Uh-oh. The quizzes.